its speed and change in angular speed, it has to take place over a certain amount of time, so why don't I just divide both sides by that same amount of time? And so my left-hand side over here, I just have my acceleration because of a change in speed, otherwise known as tangential acceleration. And that's going to be equal to delta omega over delta t, or change in angular speed over change in time, which is just my angular acceleration. That's r. That's the equation we need. And there's S is equal to complete the triplet.
What's S?
If I have an angle here, well, I actually try to get the center there. That angle, some radius, that arc length is equal to that angle in radians times the radius. That's what the top one is.
So it's the arc length.
Pardon?
It's the arc length.
Yes. Arc length is equal to the angle in radians times the radius. All right, so what do I need? I still need that. And let's get rid of this part. So my equation now becomes negative. I'm going to go ahead and do the next step. We have a formula for weight. What is the formula for weight?
Mass times the acceleration due to gravity.
So I got negative mg sine theta is equal to m times alpha r. This is still universal. We haven't done anything that would deviate from just a normal physics analysis. Mass would cancel out. So the mass, the point mass at the end is, the actual mass is irrelevant. R, I have this pendulum swinging here, and unfortunately I erased that, so let's draw part of it back. R is just the radius of this, of how far it is from the center. So that would be this length right here, which I'll just label L for length. And so my formula now has negative g sine theta is equal to L alpha. I still don't have it in a Hooke's law format, although at least I now have it in terms of both angular quantities here, but I still have this pesky sine of theta. And I'm pretty sure we talked about this 2 weeks ago. Small angle approximation. Hoping for some sign of recognition. Did I do small angle approximation 2 weeks ago?
Yes.
All right. And what is the small angle approximation telling you?
If the angle is much less than 1, then sine theta equals tan theta equals theta.
All right. So now we deviate from just the plain, from I guess sort of a pure interpretation of our analysis here. We're going to throw in a restriction here. For the simple pendulum, we have one more assumption, is that the angle is small. The angle is much less than 1. Again, no units here. We're talking about radians. So it's 50-something degrees.
So it's much less than 50-something degrees.
Yeah. So if, I guess I already have that. So if this is true, this equation here becomes negative g theta is equal to L alpha. Since alpha is the change in angular speed over time, and angular speed is the change in theta over the change in time, we now have a direct parallel to Hooke's law. Because in Hooke's law, we have something, negative something times x is equal to something times a. A is the change in speed over the change in time, and speed is the change in position over the change in time. We have a set of formulas we've already done for this, we can now apply to this.
Is the L just R?
Yes, L is the length of the pendulum. Typically, in textbooks, they generally make L the length. But it's also a radius if you want to stick with R, just so long as you know what it is. So we have negative K x is equal to MA, and the period we've done before was 2 pi square root of M over K. That was the formula that we derived from this starting point. And you can look back at your notes or review the video of how you get from here to here. For a simple pendulum, we are dealing with negative g theta is equal to L alpha. So the period would be 2 pi times the square root of, well, instead of M, I've got L. Instead of K, I've got G. And so we have the formula for the period of a simple pendulum, which we can check. Too small. Someone conveniently has left this for us. Pull it over. All right. Be helpful if it were taller. Grab one of the easy ones. All right. Oh, no. Perfect. And let me grab something more that the thing comes. Oh, there we go. I think that'll be sufficient. All right, so what I'm going to do is, hopefully, with your help, we're gonna time how long it takes to do 10 oscillations back and forth, and then we'll crank it to the formula and see how close we get. I'm pulling it back just a little bit. I'm assuming that's much less than 50 degrees, which is actually, would be somewhere around there. All right. 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Put that more centrally, so it less likely to knock it over. All right, so
21.21.
21.21,
I got 21.08.
21.
I got 20.74.
20.74, and our average.
.70 or 78?
20.70.
No, it's the last one, 20.
That's 74.
21 point, just 21, if you wanna get technical about it, 21.0075.
So,
So that was for 10 oscillations. Got the same thing?
Oh, yeah.
Okay.
I got the same.
So 2.101 is the period. Now let's find out how close we actually got to reality. Or, I guess that is reality, how close we get to prediction. So the mass of this, first off, it's not a point mass, but it's small compared to the length of it. So it's another one where we're going, yes, we can consider it a point mass because the size of that is quick and dirty, less than 10% of the overall length. We do need to know what the overall length is. And it really should go from the pivot point, which would have been about there, to the center of this. And so John, do you have a view, is that in the center down there?
Yeah, there's a little, yeah, that's it. Center of the mass? Yeah.
Middle of the mass, yeah.
Yeah.
Still close enough to the center of the mass?
Yeah.
All right, so 116.5 centimeters. So L, 116.5 centimeters. G, for this part of the world, 9.798 meters per second squared. We'll plug into our formula and hope this is not a typical physics demonstration and it will work. T is equal to 2 pi times the square root of 1.165 meters over 9.798 meters per second squared.
I got 2.167 seconds.
So we are within 3%. Let's go ahead and find percent error. Percent error would be the difference between the two, 2.167 minus 2.101, divided by the theoretical, which was this
Yeah,
2.
3%, 3.04%.
Not too bad. Recognize we now have an incredibly powerful tool. One, we can find acceleration due to gravity. By what we've done here, we're off by 3%. We can find the acceleration due to gravity anywhere that we have a stopwatch and a pendulum. And I guess a calculator or a slide rule. But more importantly, we have a timing device now. I can theoretically predict that it's gonna take a little over 2 seconds to do it. I can adjust the length to make it 2 seconds exactly if I need to. So now if it's 2 seconds to go there and back, I know it's 1 second to get to there, it's a half second to get to the bottom, so I can now do time increments in a half second. Or shorten the string, make the period smaller, and I can get even smaller ones. So I can now start getting more precise timing involved. And if we're talking 17th century Europe, which is where at least the stuff in our textbooks is coming from, the stuff that Galileo is doing, he has a way of timing now. Questions up to here? Here's 24th. Oh, we were supposed to have a quiz on chapter 13 on Wednesday. Presumably you're ready for it now. All right, I'm done with 14. So the quiz on chapter 13 was supposed to have been yesterday, but obviously I forgot. Any problem with doing it now? All right.
We should be able to finish it, like,
Pardon?
we should have time to finish it, right?
Yeah, it's just 2 questions. We got an hour.
Okay.
We'll do something afterwards. All right, let me pause this and go print it out. I'm repeating it for the camera. There we go. We got the quiz a week from today on chapter 14 and the master set due a week from Tuesday. All right, so we're talking about simple harmonic motion. And we set up the equations. This is something that we derived last week, I think, or the week before. Time has lost meaning since the pandemic. At some point before now. So we have some amplitude, which is just the maximum displacement from equilibrium times the cosine of omega t. Omega is the angular frequency. That's units of radians per second. Angular frequency. And then the velocity could be modeled by the formula negative times the, whatever the amplitude was, times omega, times the sine of omega t, and then the acceleration defined by this equation. And omega is just the square root of the spring constant divided by the point mass at the end of the spring. So that, in theory, is a recap. So when I pull the mass back and I let go, so I'm gonna set it up so that at time is 0, I'm at the maximum, which is why I can get away with cosine and no phase shift over here. Otherwise, I'd have to throw a number in after the omega t. So at time 0, I'm at my maximum value of x, or at the amplitude, I let go. Where is the mass going to be moving the fastest?
At the peak, at the lowest point.
The lowest point. It's moving sort of sideways. I'm not quite sure what you mean by that.
I thought we were still talking about pendulums.
No. Flipping back to mass on spring.
Okay.
Yes, in the case of the simple pendulum, or pendulum in general, at the bottom is where it would be going the fastest. What would be the equivalent here? Or the analog here?
We're right before the end. Like right before it hits the wall or returns back to 0.
So so it starts here, it's gonna come down here, so right before it's gonna be going fastest, just before it turns around? Is that what you were saying?
Yes.
I heard a
Before it hits the spring. Right when it hits the spring.
right when it hits the spring.
Is the spring moving this way or no?
All right, so spring sitting here, natural, that's its natural length. I then take the mass, I pull it back, and I let go. So I pull it out to here, and I let go. So this mass is now gonna be moving back and forth like this.
The
The question is, where is this mass moving the fastest?
The one right when you let it go.
Wouldn't it be about the time that it hits back, because it picks up speed, because the weight gets greater, more compressed
At what point is it not gonna be picking up speed anymore?
when it hits the wall? Well, I guess when it hits its base, however you want.
So when it's the farthest that way?
Yes, to the left.
So an object changes directions. What can you tell me about the velocity at that moment it changes direction? If it's in a one-dimensional problem, just moving back and forth. How fast is it going at the turnaround point?
0.
0, so right before it hits.
So I'm going the fastest just before I stop?
Right.
Huh, didn't feel that way.
I feel like it's the fastest when you let go of the spring. Well, when it starts.
In between the two. It's a sine wave, right?
It is a theta sine wave.
So it's gonna be in between the letting go of it and before it hits the turnaround point.
Okay, so when it starts out, I have it right here and I let go. How fast is it going when I let go?
0.
Yeah, so it's going 0 when I let go, it's going 0 when it turns around. So I'm willing to bet that the fastest speed is not 0, otherwise if it is the fastest speed, when I let go, it's just gonna sit there.
It's going to be somewhere in the middle,
We can actually be more precise than that,
the exact middle.
when it hits equilibrium.
Yeah.
It's going to be speeding up, because the net force is pulling on it. If I look at the forces acting on it, I have its weight acting down, I have the normal force acting up, and then I have a the spring force acting to the left. The spring force is gonna act to the left until I hit equilibrium, at which point that spring force goes away. And then just past equilibrium, the spring force is now in the other direction. So when it's over here, the spring force is acting that way.